Welcome to day 25 of our low-level design course. Today, we will be exploring the low-level design of a tic-tac-toe game. This session is crucial because designing a game like tic-tac-toe focuses us to think about key design principles such as modularity, scalability, and reusability. As we dive into the design process, we will apply object-oriented principles to ensure that our solution is not only functional but also clean and maintainable. Let's begin with the objectives for today's session. By the end of the lecture, you will be able to design a simple yet robust tic-tac-toe game system. We will focus on making the game modular, which means breaking the system down into smaller, manageable parts. We will also discuss how to ensure that the design is extensible so we can easily add features like an AI component or change the game's grid size. Additionally, we will explore how to implement error handling, move validation, and game reset functionality in a clean, efficient way. Before we jump into the design, let's clarify the problem statement. Our goal is to design a two-player tic-tac-toe game. The game is played on a 3x3 grid, where each player alternates placing their mark, either an cross or an 0, in a cell. The game continues until one player gets 3 marks in a row, horizontally, vertically, or diagonally, or until all cells are filled, resulting in a draw, if no player wins. The system must allow for validation of each move, detect if a player has won, and ensure that the game can be restarted after a game ends. This is a simple game, but it contains all the elements of a real-world application design, interaction between objects, state management, and game flow control. Let's start by identifying the key entities in our system. These entities represent real-world components of the game and will be modeled as classes in our design. First, we have the game class, which will be responsible for controlling the flow of the game, including alternating between players and determining when the game is over. Then we have the board class, which represents the 3x3 grid of cells. Each cell is represented by the cell class, which contains the value of the cell, either x, 0, or empty. We also have the player class, which keeps track of the player's name and symbol. Optionally, we could include a move class to handle move related information, but for simplicity, we will incorporate the move logic directly in the player class. Now that we have identified the key entities, let's take a look at the class design plan. We will begin with the cell class. Each cell will have properties like its row and column positions as well as its value, which can be 0 or x or empty. The board class will manage a 3x3 array of these cell objects. This class will include methods to display the board, check if a cell is empty, and update a cell with a player's symbol. Moving on to the player class, each player will have a name and a symbol X or O. Players will take turns making moves, and the player class will include a method for making a move on the board. Finally, the game class will handle the game logic, such as starting the game, alternating players, and checking for a winner or draw. Let's dive deeper into the cell class. Each cell needs to have a position in the grid, which can be represented by its row and column. The value attribute will store the mark placed in the cell, either X, O, or an empty state to signify an unoccupied cell. We will define two important methods for this class: the isEmpty method to check if the cell is empty, and the setValue method to assign a mark to the cell. By encapsulating the behavior of individual cells in a class, we maintain flexibility for handling grid-based logic. Moving on to the board class, which will manage the entire 3x3 grid, the board will be represented as a 2D array of cell objects. This class will include several critical methods: display board, which will print the grid to the console or GUI, isEmpty, which checks whether a specific cell is empty, and update cell, which places a player's mark in a given cell. Additionally, the board class will need methods to determine the state of the game, like checking for a winner or detecting a draw. To do this, we will check if a row, column, or diagonal contains the same symbol, which would indicate a winner. This class is essential for managing the state of the game board. The player class will represent a single player in the game. Each player has a name and a symbol X or O. The class will include methods like makeMove, which allows a player to place their symbol on the board. This method will interact with the board class to update the grid and check for a valid move. Additionally, players take turns, so this class will also include a way to alternate between players. By keeping the player logic separate in its own class, we ensure that each player's behavior is encapsulated, making the system more modular and flexible. The game class will be the central controller of the Tic-Tac-Toe game. It will manage the overall game flow by controlling the alternation between players and determining the game's state. Key methods in this class will include startGame, which initializes the board and starts the game loop, and switchPlayer, which alternates turns between the two players. We will also have validMove, which checks if a player's move is valid. After each move, the game class will check for a winner or a draw by interacting with the board class. If there's a winner, the game ends, and if all cells are filled without a winner, the game results in a draw. Here's a UML diagram that represents the relationships between the classes. As you can see, the game class has one-to-one relationship with the player class, meaning there are two players involved in each game. The game class also has a one-to-one relationship with the board class, and the board contains multiple cell objects, which is represented by the composition relationship. This structure is simple yet effective, encapsulating the logic in a manageable pieces and promoting clean design principles. Several important design concepts are applied in this architecture. First, we focus on encapsulation. Each class is responsible for its own behavior, and we avoid exposing unnecessary details to the other classes. The single responsibility principle is also evident here, as each class has a clear and focused responsibility. Board handles the grid, player handles the user's interactions, and game controls the overall game flow. We have also designed the system to be extensible by making it easy to add new features like AI or larger grids. This design promotes maintainability and scalability as the system grows. Let's take a look at a small piece of sample code from the game class, specifically the startGame method. This method initializes the game by creating the board and starting the game loop. We display the board and alternate between players, ensuring that each move is validated. After every move, we check for a winner or a draw. If a winner is found, the game ends and the winning player is announced. If no winner is found and the board is full, the game is a draw. While our basic game works perfectly, there are a number of potential enhancements we could consider. One obvious feature is adding an AI component. This would involve implementing a simple decision-making algorithm such as random move generator or something more complex like the minimax algorithm. Another enhancement could be allowing players to play on a larger grid like a 4x4 or 5x5, which would require adjusting the win condition. You could also add an undo move feature or extend the game to support remote multiplayer functionality so players can compete over a network. Your assignment for today is to implement the Tic-Tac-Toe game based on the design we discussed. Start by creating the core classes, player, cell, board, and game. Ensure that the game correctly handles turn taking, move validation, win detection, and game resetting. If you are feeling adventurous, try adding a simple AI opponent that randomly selects moves. Once you have completed your implementation, share your code with us for peer review. To summarize today's session, we have broken down the design of a tic-tac-toe game into manageable components, applying key design principles along the way. We have focused on modularity, encapsulation, and extensibility. We discussed the main entities involved in the system and their relationships, and how to implement these concepts in code. You are now ready to implement the game and extend it with additional features. Keep in mind the importance of clean, maintainable code as you move forward with your implementation. Thank you for your attention.